Thank you for watching Idealized Science Institute's long-form videos. Here, our goal is to help teachers teach purposefully. We have deliberately slowed down the process so teachers can dissect the lessons and find those hooks that will engage their students in authentic scientific practices. Now, these lessons are sequential, so please watch them in order. And if you like what we're doing, consider supporting the Idealized Science Institute. Visit our website where you could see other long-form videos, our podcast, we have quick quizzes, and so on. And as always, please put comments down below. And we are really hoping to hear from you as you enact some of these lessons in your classrooms. All right, we would have students, and this might be one of the first presentations. And you can see a lot of color here, a little pizzazz, and maybe not as much substance, but often students just don't know what to expect or what's expected from them. So let's see what they have. You'll notice pulleys are fun, not terribly descriptive. Clearly they had fun doing this, but maybe not what we're after. And if you recall, we gave the students a goal. In other words, can we find out how much work they had to do to lift each mass 20 centimeters? That's what we were hoping for. And they say, pulleys make life easy. Now, if you haven't guessed already, I wrote all of this. I'm not using actual students' work, and I can't make things as flowery as many of them might. And sometimes they're quite beautiful, the posters. But again, they might not actually tell us much about what's happened here. It says, the claim is, the less pulleys, the harder life is. We don't exactly understand what life and pulleys, what that means. Maybe that's not operationalized very well, but they do have a graph here, and notice it's got colors. You've got green, blue, and a red, looks like a trend line here. And of course, their names are prominent, and they found out that they were correct. So usually they're pretty excited about these, but these need some work. Let's just go over a few things. For instance, they have a line here for their data, and when you get down to 0 pulleys, they actually have a value. But we really can't have 0 pulleys, so that's going to be a problem here. And they do have pulleys listed here. I often look at the colors, and I'm looking for a pattern, but in this case, there is no pattern of what the colors mean. They're just trying to make it look nice. So they've done a nice job on that front, but they haven't said anything about work. So they did say pulleys would make your life easy. So we could see as we have less pulleys, there's going to be more force, but we don't actually have the numbers for those. So those are some things that we're going to point out to the students. It'd be nice to know what the values actually are. Notice we've got a lot of fluff here, and we've done an awful lot in this particular experience. So a lot of white space that's underutilized. So we'll help them out. That'll be the first iteration. Everyone can help one another. So we'll get our next one. So we have another board here, and this one is also a little bit sparse. They have a claim, and it looks like they've given themselves a check mark, probably indicating that that's correct. And they're saying more pulleys equals less work. And what I assume is happening here is they've got the raise distance, and it looks like it's always the same, and that is in centimeters, so 20 centimeters. And over here we have another, we don't actually know what this is, but I think most of us would figure it out, that for each pulley that we're adding, we're getting another 20 centimeters. And they're pointing out that these are both linear. So they have potential here. They're clearly showing that they understand, at least theoretically, what should be happening here. They also try to incorporate a picture. Now this one's not very good, and if this was a standalone poster, I don't think most would understand what this is trying to say here. I think I understand it. 3 pulleys on top, 3 pulleys on bottom, but we don't really know how that's adding to our claim of more pulleys equals more work. And then they have a few facts here. Pulleys change direction, and that is a fact. And they also said 500 grams equals 4.9 newtons. And that's some work that we did earlier. But again, we're not really answering the question of how much work are the students doing lifting that same mass each time. So we'll have the students, and they'll be able to critique each one of these posters, and they'll ask questions such as, okay, but I thought we were trying to figure out the work, and the group that made this board or whatever, they'll take that into account, and then they'll probably make another board. And again, this iterative process, we're going to get better and better. So each presentation, we expect the entire class to gain from every poster. Every poster is going to have something that's good and something that maybe has left us feeling that there should be a little bit more, left us wanting, and we'll add that, so they'll get better and better. Here we have another group, and maybe they're going to come up and present. That's what you want to do. Maybe you critique part of the class and allow everyone to express themselves, but then maybe students would like to go up and explain what's on their board, maybe after everyone's had a chance to look at them. So in this particular case, we can see they've got a nice data table, they've got their force graph, they've got their distance graph, and then they have the work done. And the group would say that it's pretty self-explanatory. The work is always the same. You can see how they got the same exact value, 0.98 joules every time, and it's clearly shown on that graph. So every pulley system is doing the same thing. And this looks really good in terms of the data table and the charts. But we're probably going to have some critiques, especially from the groups that were critiqued earlier. They might ask, they might say, well, one of the things that you're missing on yours is a claim. What was the claim? And they might say, are there any facts that we should know? Like, exactly what does pulley 1 mean, or what does pulley 5 mean? And those that made this board might say, well, I think everyone understands that. But if you remember, part of our goal was to have some standalone so that anyone could come up, understand what's going on. And this happens at science conferences. If you have a poster or something like that, maybe you're not there. People are going to come around and look at your poster. If they can't figure out what it's actually about, it's probably not very meaningful. So while this one looks really good, it really doesn't tell us the claim, so we probably would add something about that. And we also critiqued another group that was trying to draw the pulley system out. While we all think we understand what pulleys are, one student might raise their hand and say, wait, we started with 2 pulleys. And others would say, we did too. Now, this group would say, no, we only had 1 pulley up top. And they would say, well, we also had that pulley down at the bottom. And this group would say, well, that one just changes direction. And the other group would say, well, we called it pulley 2. That's how we operationalized ours. So all of these comments are going to help the next group that thinks, well, there's some really good aspects about this particular board, but there were good things about the others. This one might even need a little pizzazz. But one student finally raises his hand and says, isn't this what we did together? And the group said, yes, that's why we put this together. We found out, theoretically, that we're going to have an inverse curve, and theoretically, we're going to end up having a linear curve, and here we're just going to have the work being the same. At this point, others are going to say, yeah, but we were supposed to find out what we got. And the teacher would then probably jump on board and say, yeah, that's what we were asking. We understand the theoretical claim, but in terms of what you actually did, when you pulled these, when you measured these, that's why we went back around and we remeasured everything. So all of this is a very, very nice summary of what we think theoretically is going to happen. But again, we wanted it experimentally. So we'll see what the next group does. It's time for another group, and this group will come up and present. The group would then say, look, we've operationalized what we're doing with our spring scale, our mass. You can see a pulley up top, a pulley down below, and they're connected. We also have a blue pulley, and that's color-coded because all of our pulleys that we used are blue, and we noted that they are really not counted in our counting scheme of pulley 1, pulley 2, pulley 3. They're just changing the direction so that we could pull the spring scale up. We've also tried to show that we're lifting the 1/2 kilogram up 20 centimeters, and we used a large D for that. that is always going to be the same for each and every pull. However, the small d, that's the distance that we're pulling. You know, we have to pull the rope up. And then for our pulley numbers, we were using pulley numbers before, but we noticed the last group, we had time to fix this. What we mean by pulley 1 is just one single pulley, and notice it's up top. This configuration over here is a pulley on top and a pulley on bottom. So our example here is a 1-1, pulley on top, pulley on bottom. And we're going to start using this notation. And we overheard other groups also talking about something similar, so we should give them credit. We then had our force, and that is off our Newton scale. In terms of our distance, we have our small and our large d. Remember, we said that this d right here is always going to be raising that heavy mass the same amount, that 20 centimeters each time. And this small d is what we pulled. And when we took our force times our distance, we got 1 for each one of these. And we put a few notes over here. We also color-coded distance for this middle graph so that you would know what we were talking about. And that also aligns with the color coding over here. And we could see that our force drops down. We had already said theoretically that it's going to be an inverse. Our distance is going to end up being linear, and the work is all the same. So, any questions? The teacher would come back in, and you would simply let students ask questions. And I imagine almost all of the students in the classroom are going to be very, very happy with this. We've really made a lot of strides here. So we've got levels of detail that we didn't have on any other presentation. We have spring scales, and you could see it reads 0 to 5. I think that's fantastic. They also showed a little calculation of the weight. They knew that. Again, taking care of those blue pulleys. I like the touch of using the orangish colored rope that we used. Now, it doesn't have any real significance, but since everyone was using orange rope, and I'm assuming because we don't have any orange whiteboard markers, they're not going to use that. Okay, so we now have a table. We could see their values. We can also see their graphs. And almost all of the questions and comments from the classmates at this point are going to be really congratulatory on what a nice job they've done. This is head and shoulders above anyone else's. So with that, we're going to let the students think about this just for a moment. We can see serious progression with our students in making their boards and posters. And this last one was bringing elements from all the other critiques. And again, an excellent job. Every student is contributing to the best of their ability. So there's a balance here. You have to balance how much that you're able to critique students while still letting them feel really good about their work. In case you didn't notice, there's some serious problems with this board. There's some assumptions that they made. The other students haven't seen it yet, or they haven't registered it yet. Or maybe they did and they didn't want to say anything. So at this point, you're going to try your best to have that balance of making them feel very good for the work that they've done, at the same time being able to point out maybe some inconsistencies. Let's see how to do that. Okay, now that we've had a little bit of time to analyze this data table and also the graphs, let's point out some things that we really loved about this. I'll point out that pulleys versus work, pulleys versus distance, and then we also have the pulleys versus our force. Well done. Color coding looks great. Love the color coding up on the table along with the pictures here. Just a fantastic job overall. So as a class, we're going to try to see if we can put this to a test and see how well it can stand. Again, great job. But I just wanted to have one question for the group, and that was, I noticed that there was one significant figure here, 3 significant figures here, and 1 significant figure here. And for those that don't know what I mean by significant figures, notice that we have 3 numbers here, we have 2 numbers here, and just 1 number there. And the group might then say, oh, well, we didn't really worry too much about significant figures with the distance. We already knew that the distance has to follow. It was evident in our theoretical work that you can't create rope. So you're either going to have 20, if I pull down on 20, I'm going to have 20 go up here. And then we found that pattern is going to work with every pulley. In other words, it's got to be 40, it's got to be 60, it's got to be 80. And so we mark those as such. The teacher looks around and almost everyone in the class agrees. As a teacher, you're probably going to agree also. Once you know that you can't create nor destroy rope over a pulley, it's really hard not to measure these correctly. So as a class, as a community of learners, we would probably all say, we get it and that makes sense. So the teacher might press a little bit more and say, yeah, so you have 5.0 and then you're going to multiply that by the distance that you pulled, and that would be 5 times a fifth, and that gives 1, so that's very good. Now, you look in the class, everyone's nodding in agreement, and they're confident. They're feeling good about this. However, even without a calculator, I can see this one is going to be 1.0 multiplied by 1.3. Now, the group would say, oh, well, yeah, it's 1.3, but 1.3 rounds to 1.0. And we also knew that our work has to be the same for each one of these. Teacher looks around. Some in the class are a little bit skeptical now because 1.3 and 1.1 times 1.2, that gives us a little bit of an uneasy feeling. Maybe we need to look in that a little bit deeper. And you're looking at the forces, and you say, oh, by the way, you did a fantastic job of showing us that you used that 0 to 5 scale, and you drew that in. And they said, yeah, it was great. We used it for pretty much all of them. Now, a few eyes are going to widen when they say that, because it appears that they've always used the 0 to 5. But now they're saying maybe they didn't always use that. So now we're starting to think, something might not be totally correct about this. And they also have some notes over here, difficult pull, easy pull. But again, this seems a little bit odd to me. And so you might give the students a chance to say a little bit more. So you might ask them, you said you didn't always use that scale. And they said, yeah. On the first time we pulled on that just one pulley, when we had one pulley up top, this configuration. Like when you pull a spring scale, you can pull it and it'll go below that 5. Sometimes when you're lowering the mass down, it'll read a little less than that 4.9. So we had to use the 20, the 0 to 20 scale on the very first one. So we didn't use the 0 to 5 on all of them. And we could only really see that it was 5 because it was going a little bit more, but we couldn't really measure it, so we just said 5. Now, other students are going to say, yeah, we had that same problem because depending on how you pull the spring scale, you can kind of get whatever number you want. Now, this group is saying, yeah, that's what we did here, is we got our highest value. Like if you're pulling it up, sometimes it'll go and give you a larger value. And if you stop, it might be a different value. And if you're lowering it down, even without it moving, there's like enough friction in those pulleys that you can kind of get it stuck there. And if it's moving, it changes a little bit. All right, so right there, we are now saying, wait, where is that information on any of this? That's a crucial piece that needs to be on there. So we're going to give everyone a few minutes to think about how we can incorporate that to make this as honest as we can with this table. This table, the charts, diagrams. All right, so now we're in this situation where we have the group that's pushed us forward the most is now in a peculiar state, in that there's some real inconsistencies, some things that we need to take care of. So you need to make sure that you're honoring their work and letting them know that they pushed us forward so that we could see a little bit further to get a little bit better. And it's really important that you do that, because you do not want students giving it their all, doing really, really quality work as high as they can go, and yet it's a necessary piece. This is how science advances. Critique is what science is. Peer review. Finding those, things that aren't making complete sense so we can make them even better. So we're going to delicately work through this, and as a community of learners, we're going to all move forward together. All right, the class discussed what we want to do, and it turns out that many other groups had also assumed that the work had to be the same for all of the pulley systems. And some of them had admitted that they actually went back and they had a range also, which we're going to show right here. So I'm going to put my maximum value right here, and then my minimum value. Blue would be minimum, red would be maximum. And some of the other groups said, well, we knew what we needed it to be, so we just picked the value in between there that would give us the work that would always be close to that 1 or 1.1, whatever it was. That happens all the time. We have to be very careful. Remember, that was our theoretical idea that said all the work should be the same. But when we do this practically, it's not. And we could see our minimum values and our maximum values. We decided to use red and blue. Now I can even go back and make this diagram, which is fantastic, even better. Let's look at the two here. I have a 2.5 and a 2.9. So over here I could end up putting my 2.9. I'll put a little red mark there. And we could say this is going to be our 2.5 right there. So we can see that there's going to be a difference between what that scale can read. Crucial that we let people know that. So you could see 2.5, 2.9. In fact, it's so important that we might even want to write that in. So 2.5, 2.9. And this one's 2.9. And that way we can show there's a max and a min. Those pulleys have some stiction to them. So in other words, you have to break them loose to get them to move. And, they're not frictionless, and these are not ball bearings or anything like that. Now that we have our range, we can then go back and put our range. Here was our average value that they calculated before. It's fine to leave that. We just left it there. But now we're showing the maximum values and the minimum values we can get. That's going to, in turn, change our work that we've done. Notice that this is the minimum work we've done. In other words, we'll take that force times our distances just like we did before. But now you can see there's a minimum and a maximum. And even if you try to make this the same straight across, you really can't. Especially with that last pulley configuration 6. And as much as we don't want to, as much as we want to go with our initial idea that they have to be the same, we have to be very careful, because this bias creeps in all the time in science. And it's often unconscious. Here, for some of our students, it was their first time going through something like this, and they might have purposely done this. But even seasoned scientists have to be very careful of not trying to make the data to what they want it to be, and accepting what it is. Crucial. Now, why is this? Why is the work actually going up as we end up adding pulleys? You give the students some time to think about this. But this is the answer right here. This is a big chunk of metal. Remember, we're using these metal pulleys. We are not just lifting that 500 kilograms. we're also, or at 500 grams, we're also lifting this set of pulleys. And this set of pulleys has a significant amount of mass. In fact, this is over 100 grams. So when you have the 3 pulleys on bottom, you're not just lifting 500 grams, you're lifting actually 600. I think it's actually going to be 620. Hence the reason why we are doing more work when we add a higher pulley configuration. And it kind of explains why we're getting that stair stepping. Remember, we should get our first stair step here, and then these two should be about the same. And we kind of see that on our data. So really, really important. Anytime you're doing experimentalism, being honest and being careful of any bias that might creep in. Overall, a fantastic job by the students, and we can get better and better each time we do this. What a valuable lesson. If you can take your students all the way through this, this is just going to be transformative. They'll never be able to think with absolute certainty about their work again. And you might think, well, isn't that bad? We're going to destroy our students' confidence. We're not destroying our students' confidence. We're actually going to make them more confident about their understanding of science, in that we're never going to get the exact answer. There's almost always a level of uncertainty, a range that we can say that we have confidence it's in between. And trust me, if you're ever going to publish something in a journal, you would do anything to keep from having to retract after something is published data that was maybe not analyzed correctly or collected appropriately. So it is crucial. It is a crucial aspect of science that we dig deep. We look at how things were analyzed. We look at how things were measured. We ask questions. You maintain that skepticism as you're going through this. And you don't just buy into authority. That other group was doing a great job, but every group, every scientist has the same type of human bias that we want things to be one way. But we have to make sure as scientists we're reporting how they actually are. All right, let's call it a day.